W, and V. Cool. All right. I'm waiting for question? No? Okay. Everyone feeling good about this? Still kind of mid-review, kind of everything looking familiar? Nod your heads if this is yes. Shake your heads if this is no. Okay, great. Perfect. All right, so we've defined the cross product, and now we just need to know how to find it. There is a nice handy-dandy formula for it, and that is going to be given by something straightforward. So V cross W is equal to, right now it's going to look a little ugly, but I'll make it nicer soon. V2W3 minus and V3W2. That's a scalar number, right? This is just multiplication of the components. And this is the directional vector I, right? So let me just write up here, I, J, and K. The I, J, and K are going to represent our unit vectors in the direction of our coordinate axes. So I is the x-valued x-coordinate base vector, J is the y-coordinate base vector, K is the z-coordinate base vector. It's okay? It's okay? Okay, good. And this is going to be a minus here, negative, and I think, let's see. I think I can do this if I do it like this. J plus, I'm setting up my boundaries first. So whenever you work on a problem, try and set up your boundaries first. By the way, if you're going to draw a picture, try and set up the biggest point farthest away you can and work in. If you're going to build a building, try and figure out how far you're going to have to go up first and work your way, you know. Don't just keep building up and eventually it stops. That's how the Tower of Babel happened. And look what happened from there. All right, so we have this number here times that, and this one is, if I remember correctly, yeah, V1 W3 minus V3 W1. And this guy here is V1 W2 minus V2 W1. And we have a really quick and easy way of writing it with something called determinants from linear algebra. Everyone familiar with determinants? Raise your hand. Okay, cool. So the determinant of a matrix A, B, C, D is, in this case, if it's a 2 by 2, the determinant of this matrix is just A, D minus B, C. So I can rewrite all of these guys in terms of determinants. So I'm going to write determinant of V2, V3, W2, W3, I, minus determinant of V1, V3, W1, W3, J. These are all arrowed, plus determinant of V1, V2, W1, W2, K.
Which is the determinant of the 3 matrix.
Which is a determinant of a symbolic 3 by 3 matrix, which I'll write next. So when you start out with determinants, all you really need to know is this handy little guy, the determinant of a 2 by 2 matrix. And then there's a rule for how to take a determinant of any bigger matrix, which I'm not going to go through right now. You can read it in your text. It's in the cross product section. But in short, the cross product is determined by the determinant of a large matrix, I, J, K, times V1, V2, V3, W1, W2, W3. And it's important to note that this is a symbolic matrix. For those who've taken linear algebra, there's something that fails about this. You don't get to have vector entries in a 2 by 2 matrix, in a 2D matrix. It's symbolic, but it's very, very helpful. It makes it super easy to remember once you get the problem down. Okay, so quickly we'll go through some of the properties of cross products here. 15. but you guys know it already, so I really just have to kind of say it. So properties of the cross product. Some interesting ones. So V cross W, excuse me, I want to go the other way around. What if I switch my V and my W? So if I have V and W, and say my cross product's there, what if I switched which way I was looking at them, and I had W and V?
Then it'd be equal to negative, right?
Then our right hand would have to turn the other way around, right? And our thumb would end up pointing down. So W cross V, when I switch the order of a cross product, I actually have to negate the sign of the cross product. And this is called being anti-commutative. Yeah. And 2, the cross product of a vector with itself is the 0 vector. Yeah. What's orthogonal to a single vector? Well, only the 0 vector is orthogonal to just one vector. 3, we have, what does it take for the cross product of 2 vectors to equal the 0 vector? That's a different question, right? If 2 vectors have the 0 vector as their cross product, they could be the same vector, or they could, this is happening if and only if V is equal to some scalar multiple of W. So the cross product of 2 vectors is 0 if and only if they lie on the same line, right? V being a multiple of W means that V is on the same line as W. So here's V and here's W, then their cross product is 0. Yeah?
Could they also be parallel?
That is parallel, yeah. Yeah.
Okay.
They're definitely parallel there. So if you're parallel, you do lie on the same line. So maybe you are an affine translate of another, right? Maybe you've translated it. From the point of view of cross product, it really doesn't care. You want to make sure it's on the same base point, you would subtract one over to the other, and you'd be good. Yep. 4, we have that constants pull out, just like in the dot product. And 5, distribution holds. So we have V cross W plus, and what did I do? Z equals V cross W plus V cross C. So you can distribute as well. Notice, though, that these two things aren't equal. Even though I can distribute across, I can't switch the order of this cross product, right? That is totally causes the direction to go blah, the other way. So I can distribute on the left and I can distribute on the right. But those two things are not equal. They're, in fact, opposite in sign. All right? So, yeah.
For number 3, is that a 0 or a C?
This is a C, constant.
Constant, okay.
They've been using lambdas in the text. Would you guys mind if I use lambdas? All right, I'm going to use lambdas from here on out. Lambdas are constants. Okay, great. I'm going to review now some formulas for lines and planes. Some sweet formulas for lines and planes. I'm going to erase that over there. Is that okay, guys? Yeah? Okay, good.
How come this only works in 3 dimensions and 7?
I don't know.
I kind of want to look at that later. So if
I think, my guess is it's a hard mathematical proof. So this is an example for those of you who are like super into math of something called a Lie bracket. So something called a Lie algebra is a sweet thing used to describe lots of physical real-world properties. And a Lie bracket is an operation you use in it. A Lie bracket requires certain things to happen. And my guess is in 2D and 4D and 5D, it just doesn't work out. But I don't know why.
I guess one of the simplest levels is just that I'm not certain that determinant formula would work.
Well, it should in any dimension.
But you need a square matrix though.
So when you do written problem 1, you're going to try and derive the cross product. As you're going along, why don't you try it with 4D and stuff like that? All right, so formulas of lines and planes. Again, this is just to recall, we are probably going to feel pretty familiar with all of these things already. So just for a line, and this is in 3D. So formula for a line that goes through some given point, P0, and we'll call that, what are we calling it? X0, Y0, Z0. So if your line in three-dimensional space goes through some particular P0 point and has some particular direction, again given by some other vector, here it's given by W equals W1, W2, W3. So here we are in 3 space. You're going through P0 here in the direction of W. And a formula for it is given by maybe a line of T equals P0 plus T times W. So that's the vector form of the line, right? An equation for a line is a point plus all multiples of the vector that goes through that point in the direction we want. So here's that point. Here's all possible multiples T of the vector we have, the direction vector. But that's not very suggestive, so let's go ahead and write out what it would be in terms of x, y, z coordinates. P0 is base point x0, y0, z0, plus T times W1, W2, W3. And if I multiply T onto all these W1 components and sum them up, I get my, I guess, what do they call them? They call them component formulas, right? I get 3 component formulas for the x position, y position, and z position based on time t. So y0 plus t w2, and yeah, and z0 plus t w3. So that should be pretty familiar, pretty much like, oh, okay, yeah, that's fine. That's a line in 3D space. Plane is going to be a little bit more difficult, but not too much more so. A plane is defined by a point in it and a vector, which we're calling a normal vector, orthogonal to it. Orthogonal. Cool. You guys are champs. You doing good? We're cramming a lot of review session in here, so bear with me another 5 minutes. So a plane is defined by a point in it. That makes some sense. I'm down with that. So here we are in 3D space. It has, what am I calling it here? I'm calling it still P0. It's defined by a point in it and a vector orthogonal to it called the norm, right? Could be hard to figure out a formula for the plane in general, but we know that there's some vector here that's orthogonal to any vector that lies in the plane. All right, so let's call this some unknown point in the plane. If we are doing our typical vector thing, well, this is the vector origin to P0. This is the vector origin to P. This vector here, then, is the vector